Welcome to our channel. Now we are moving to the capacitors. Okay, so still now we completed the resistor as well as inductor. So in case of capacitor, apart from the resistor, capacitor is also basic component commonly used in electronic circuits, right? What capacitor is doing? The capacitor is doing the ability to store charge. In this particular capacitor you are using the stored charge. But in case of resistor as well as inductors cannot do, because resistor only consume the energy, right? It dissipate the power. In case of inductor, it store the electricity in the form of magnetic field and relieve due to the self induction, again it is relieved back. So but only capacitor can do store the charge. Okay, next very important point. This is one of the question from the previous paper. We are going to discuss that. So one of the important point here, this is the previous paper, opposes any change of voltage in the circuit which is connected to it. That means capacitor opposes the change of voltage. Okay, I will give the 3 points here. Resistor opposes the flow of current, and inductor opposes a sudden change in current. Capacitor opposes the change of voltage. Okay, now it blocks the direct current flowing through it. It is also blocks the direct current flowing through it. These 3 points are important, you should remember. Then this is the representation of capacitor having a 2 plates, conducting plates, in between dielectric media present. Dielectric media, maybe air is a dielectric media, mica is a dielectric media, ceramic is a dielectric media, paper is a dielectric media. Like any dielectric media can placed in between them. So this is a representation about the capacitor. So capacitors are manufactured in various sizes, shapes. Their values are used in hundreds of purposes. Okay, so many applications we have. Essentially, capacitor consists of two conducting plates. Just now I mentioned it's separated by the insulating media is called as a dielectric, that one. So dielectric could be air, just now I mentioned mica, ceramic, paper, polyester, polystyrene, or polycarbonate, plastic, etc. Those are the dielectric medias. Okay, so this is about the introduction. Now we are moving to the how exactly the capacitor is working. Look at here, I will explain clearly. Capacitor connected to, for example, initially capacitor is a discharge. There is no charging in the capacitor. Okay, now switch is closed, right? Now switch is closed, that means this is the condition. Whenever switch is closed, V is connected across that. Initially, this is a positive terminal, this is a negative terminal. That means this particular plate, initially this particular place, there is no polarity. Due to this positive supply connected here, it try to attract the negative, that means electrons towards this particular plate. Similarly, this is a negative here connected. Whenever this negative is connected, it is trying to attract the positive ions, that is holes, towards the negative plate. Okay, so this is happened whenever you increase the voltage. This is happened continuously. So whenever it reaches the maximum position, that means maximum charge in between them, so it will be equivalent opposite charge applied across this particular voltage. That means whenever it reaches to the maximum voltage, it the polarities are positive and negative. This positive polarity opposite to the supply voltage. Okay, that means it is a fully charged. Whenever it is fully charged, the charging current, the supplied from the charging current are reduced. Initially, for example, see here. So it is a time, it is a current. For example, charging current, like that. Whenever initially charging current increases maximum, whenever it reaches to maximum, so charging current going to be decreases. So for example, it is a charging. Whenever it is connected to the load, it is discharging, like the capacitor current. Coming to here, this is whenever it is completely discharged. For example, this particular supply is disconnected, you are connected to some other load in the circuit. So this capacitor trying to deliver the current in this direction. and then whenever it's trying to deliver the current, now capacitor totally discharge. Okay, whenever for example you are short circuit these two terminals, definitely it is going to be discharge. So this is about the just basic idea about the capacitor, how it is charging, how it is discharging. Okay, so you need to remember few points related to that. The first point, there is no current flowing through the, okay, first point, there is no current flowing through the dielectric media. No, no current flowing through the capacitor because we have a dielectric media. So there is no current flowing through capacitor. Why? Because in between dielectric media is present. Because of the presence of dielectric media, right? So next point you need to remember, whenever just now I explained, whenever it is potential difference, the potential difference means that the M and N have a potential difference. Whenever potential difference occur, the charging current, the dielectric media charge the current. Okay, whenever it reaches to the maximum charging, so maximum potential difference, then the charging current is going to be decreases. So here the point here to remember, the one of the concept is dielectric strength. For example, I will explain what is mean by dielectric strength. For example, it is designed for 5 volt, but you are connected to 7 volt to 10 volt. For example, you are trying to give. So capacitor is working fine up to 5 volt. For example, you are increase the voltage more than the 5 volt. What will happen? The capacitor is trying to charge up to 5 volt. After that, spark going to be occur. This particular dielectric media is breakdown. This dielectric media is a breakdown. Whenever it is a breakdown, so capacitor going to be damaged, short circuit like that. So that means that whenever dielectric strength is a maximum strength withstand the applied voltage. So the units of dielectric media, volt per meter. The another unit is also in practical applications kV per mm. Okay, maybe in the power systems it is going to be used this particular formulas, kV per mm or volt per meter. Okay, next point you need to remember, whenever potential difference exists between the two plates, electric field set up between them. Yes or no? Whenever these two media, whenever potential difference occur, definitely electric field will be created. So that field strength, the formula for field strength, you need to remember that E is equal to voltage divided by distance D. So that is a volt per meter. That is a electric field strength. These points are what I gave, the particular formulas or points are very, very important. You may expect some questions from this examination. Okay, clear? So that's what the capacitor connected to battery concept. Then we are moving to the then we are moving to the capacitance. So so in the case of capacitance, it is measure the ability of capacitors to store charge. Okay, now it may be defined as, the capacitance may be defined as amount of charge required to create the unit potential difference between them. Okay, that is the definition of capacitance in general. That is C is equal to Q by V. Very, very important. Everyone remember the units of capacitance is farad. Okay, so how to define this capacitance. For example, 1 farad capacitance is defined as the capacitance of capacitor which requires the charge of 1 coulomb to establish the potential difference of 1 volt. Okay, establish the potential difference of 1 volt in between the plates. That is called as a capacitance for 1 farad. Okay, next, Capacitor may also defined, very very important, defined as a property to oppose, just now, oppose the change of voltage in the circuit. Capacitor opposes a change of voltage in the circuit. From that, C is equal to change of opposite voltage. C is equal to I into dV by dt. How this formula you got? So I is equal to C into dV by dt. This is a basic formula. From that formula, the capacitance C is equal to I divided by dV by dt. Okay, so from that, you can also define the capacitance. 1 farad of capacitance can be defined as which causes 1 ampere charge, yes, 1 ampere charge current to flow when applied voltage across the capacitor changes the rate of 1 volt. This is the rate of 1 volt. That is also capacitance. C is equal to I into dV by dt. Okay, these formulas are already known formulas, just I recapitulated because in your intermediate as well as in your BTech everything you know all these concepts, but basic idea what I gave these formulas to you, each and every formula, because you are attending the objective examination. In the objective examination you can't expect the questions from directly from the some defined bits you are by heart and go to the exam. That is not a successful formula. We have to analyze the subject, analyze the formulas, everything from the point to point in the syllabus, then only can success in the examination. Don't even hurry up you to no memorize the formulas also. Just understand the concept, after that note down the formulas and memorize it. Okay, then we are moving to the another thing. In case of capacitors, the values, different values you mentioned, but it is usually small values. It can be mentioned 1 microfarad, for example, the units. 1 microfarad means 1 into 10 power minus 16 farad. Okay, so next 1 nanofarad. Nano is nothing but a 10 power minus 9, 10 power minus 9 farad. Okay, another thing, picofarad. These are the representation, various representation related to the capacitance. 10 pico is nothing but a 10 to the minus 12 farad. Okay, so this is about the different notations for the capacitance, different values. For example, very small size nano or picofarad capacitors are there in the practically. Okay, then we are moving to the factors controlling the capacitances. It is also very very important. You can expect the question from here. So factors controlling the capacitance. So various factors we have. First factor is area. First factor is area. So how area is related to the capacitor? This is a capacitor representation, right? This is the first plate, this is the second plate. Okay, so the area covered in between it is a distance. Okay, the area, this particular plates we have area covered. So the area is directly proportional to the capacitance. That means capacitance is directly proportional to the, okay, so here capacitance is directly proportional to the area of the plates. So when our plate area increases, what will happen? Capacitance also increases. So here A is a area of plates. Okay, C is a capacitance. So first thing is done. Next, second parameter. Second parameter is a distance, plate separation. Okay, for example, this is a capacitor. We are increase the distance. This separation from these two plates are increases further. What will happen? So whenever I increases the plate distance, let me increase the plate distance separation. So whenever separation is taking place, that means more dielectric media is present. What will happen here? Capacitance value decreases. That means capacitance is inversely proportional to the separation. Okay, whenever distance increases, what will happen? Capacitance decreases. Whenever distance decreases, capacitor increases. Both are inversely relation. So next one, next we are moving to the next third one. You need to remember, for example, you are using air as a media. So permittivity or dielectric strength is different for area, mica and remaining. So whenever you are thinner dielectric strength, thinner material, dielectric material you are using, capacitance may increases. Separation increases, capacitance decreases, but dielectric media strength increases. That means we are using the thin dielectric media. What will happen? Capacitance also increases if you are using the thinner dielectric media. Okay, next one, fourth one. I'll have to clear about that. Fourth one, type of dielectric media. Just now I mentioned type of dielectric media. Okay, so just now capacitance are inversely proportional to distance or thin dielectric media, more capacitance, thin. So coming to the dielectric media, type of dielectric media, for example, it depends upon the relative permittivity, not permeability. In case of inductor, I am discussing about the permeability or permittivity. So everyone clearly listen. Epsilon R is a relative permittivity. Relative permittivity. Okay, so it is also depending upon the epsilon R on the dielectric media. Higher the value of epsilon R, what will happen? The capacitance is also higher. So we know all these three combination combined together, capacitance is equal to epsilon naught epsilon R A by D. Okay, here epsilon naught is a absolute permeability. Here epsilon naught is a absolute permeability. Permittivity. Okay, permeability is different, permittivity is different. So in general, epsilon naught value is a constant. That value is a 8.5854 into 10 power minus 12 farad per meter. Okay, that is about the epsilon naught value. That is a constant for every material. Then we are moving to the what is the values. Then we are moving to the what is the values of different dielectric media permittivity, relative permittivity. So here this is the table you need to remember. Air or vacuum permittivity is 1. So epsilon R is equal to 1 in case of air or vacuum. In case of backlight, 4.5 to 5.5. In case of ceramic, 50 to 3000. In case of fiber, 5 to 8. In case of glass, 7 to 8. In case of mica, 3 to 6. Paper, 3 to 5. Polystyrene, 2.6. Porcelain, 5.6. Okay, 5 to 6. So this is about the values you need to remember. Okay, then we are going to discuss one problem related to that. So that problem, what is the capacitance of capacitor if charging current of 100 milliamperes flow when applied voltage changes 20 volts at a frequency of 50 Hz? Okay, this is a problem. Still now we discuss some formulas, right? In this particular problem, they mention the current that will be 100 milliamperes. Change of voltage. So V is equal to 20 volt and frequency is equal to 50 Hz. That can be converted into time. T is equal to 1 by F, that is a 1 by 50, that is equal to 0.02 seconds. Time also. From that, you want the capacitance value. C is equal to, just now I gave formula 1 by dV by dt, right? So that is I by dV by dt. I is a, so let us substitute the values here. I is equal to 100 milliamperes. So 100 milliamperes divided by dV by dt 20 divided by time 0.02. Okay, that will be equivalent to 100 microfarad. Okay, so this type of problems may be in the examination. So that's what it is, a part 1 for the capacitance. Then we are moving to the part 2 of capacitance. The part 2 will discuss the different type of capacitors. Thank you.